Okay, good morning, guys. So you may now chat your attendance in the chat box. You type your last name, first name, and your ID number. Okay, ang ma-record naman sa attendance kaya ang naturang ang ma-apila sa attendance katong na-record. Okay? So, nanabi nag-type silang pangalan?
Ito, konti na akong ipagkita gabon, sir.
Okay, okay na to ba?
Salamat kayo, sir. Thank you, sir.
Sige, dayon. I'm going to share okay, so use that. Okay, so welcome to Process Automation 2, EMP421. Then we are now nanatadali sa March 21 a week, no? So you may download this file, no? PID control mode, proportional derivative. Okay, so I'm going to share my slides. Okay, so can you see my slides, guys? Kita naman eh. Sikuan. Okay. Okay. So, again, no? Ito ang discussion is just a continuation of the different PID control modes, no? That can be set or programmed by the PID controllers. So, mananataning on and off, proportional control, mananataning PI, proportional integral control. Then, I added the sipyat din eh. This is PD, proportional derivative control. Yara, sipyat ito, proportional derivative control. Okay, save. Share the screen. So let me share it. Okay, so we are now in this proportional derivative control or differential control. Okay, so what is a proportional derivative or proportional differential control? So technically, the proportional word is the proportional controller added by the derivative controller. Okay, so it combines the proportional and derivative or differential actions to provide an immediate response that is not only proportional to the error signal but also anticipates the error signal based on how quickly the error is changing. Okay, so pag mingon ka differential or derivative, it is actually anticipating, no, kanang advance ba? Bali siguro kung if we're going to compare or make an analogy between the weather condition as to the PID controller, ang P mao na ang imong present na value, no, present na weather condition. Ang imong I, no, which is the integral, is actually the previous na mga values, no, or mga katong past na mga weather na conditions, katong ng labay na. Whereas the differential is money ang forecast, no? Forecast for the today or future siya. May pasabot na anticipates the error signal, no? Anticipate pasabot kung sa pista pa anti-pista or anti-dispiras, na nila na term, or dispiras, no, sa pista. So I hope masabtan mo, no, i-combine naman nato ang kuan P, I, o D. So, mananata sa P, mananata sa I, then karon D na. No? So, ang P is present, the I is ang ganing yesterday, the past, and the D is the future. So, mana pasabot anticipate. Okay? I hope na ma-relate na ninyo into layman's term. Okay, so this is again the block diagram, no? Process control system diagram for a PD, no? Proportional derivative na controller. So, notice ninyo na it's just a combination of proportional and derivative or differential. The controller calculates the error and determines the combination of proportional action and derivative action necessary to correct the error. Okay? So kung tanaw na to ni ato ang kuan, example diri na mao ni atong error, no? Atong error is constant for quite some time, then naglinear din siya. Naglinear din siya. Then this is the controller output. So duay ang output na ay proportional o napoy derivative. Color green ang derivative, then the proportional is blue. Okay? So matingala mo, sir, ano duha mga output? Because it's a combination of proportional derivative control system. Okay, so during the operation, the derivative control action leads the proportional control action by a certain amount of time called derivative time or TD. So ano yung time elapsed niya. Okay? Then, mga niya mga different na mga responses, no? From error. No? Error, na kay inani na error o na kay dugay-dugay na error, unsa imong response sa imong derivative response. So let's analyze kani error changes at fast rate relative to the color green. So saka siya, no? Faster siya as compared sa green. So ang imong controller kay derivative man. So what is the derivative of x? Let's say mga nito ang kuan, no? To equation of the line, x siya assuming. What is the derivative of x? Kadumdum pa mo, what is the derivative of a variable x? So ang derivative niya na constant, no? Pag-derive ni mga x with itself is constant. So manang ikalit ng siya saka. Kalit siya saka. Kalit kayo, no? Sudden saka niya, no? Large step change or large siya kay taas-taas man eh. Kalit na siya. Instead na linear pa siya dere, ay mo na siya constant diretso. Okay? Dayon, pag slow, no? Slow ang imong rate sa pagsaka sa imong line. So ang iyapong output constant yapon, no? Pero small step change. Small step. So ingon dere, the derivative control or rate control adjusts the controller output based on the rate at which the error is changing. So kani pas-pas ang iyang rate, fast rate, and this is slow rate. This causes the controller to anticipate what error will become and will try to prevent it. Okay, so ang error na nakapasaka man, no? So anticipate niya ay constant na niya diretso. Constant na yun. Constant na. Dari po, anam-anam. So wala pa siya kasaka sa layo. Anticipate na niya na agoy magkadakwang error. So applying derivative or differential, so may mo siya constant. Or what is known as step change. Step change. To prevent the error from increasing. Okay, so maorman lang ganyan, no? Mani ang derivative time. Derivative time is a value that is programmed into the controller. Okay? So pag mag-program ta sa derivative na parameter sa controller, mo din siya the derivative time. So mo na tayo program. So you notice as the derivative time increases, the derivative action also increases. Pareha to ganiyan. Mataas po siya ganun. Mataas ang iyang output or step niya. Okay. So unsay pasabot ani na figure? Anybody would like to interpret the figure? 17 mo nakabuk dito na no or ka-18 siguro ko. So unsay pasabot ani? So you have an error, no? So mao ni mga output, no? Mao ni mga process variable, mao ni mga output. I know set point it's below the process variable, no? So there is what is known as an offset error. Okay? So the question is, you have a constant error, no? Or steady state na condition. What is now the output of your derivative controller? Sa kay output sa imong derivative controller. So what is the derivative of a constant? Kadumdum ba mo? Okay, so the derivative or the differential of a constant is actually 0. Okay, so kung ang integral sa 0 is constant, ang derivative sa constant is 0. So baylo-baylo na sila. Pag i-integrate nimo ang 0 or antiderivative, may mo constant. Pag i-differentiate nimo ang constant, may mo 0. So ano siya? Integral and derivative. Integral is also known as antiderivative. Okay, I hope na na-appreciate niyo yung calculus. Okay, so the derivative control is not used alone because it only contributes to the response if the error is changing. So notice na wala siya ma-anticipate ani kung ano man because ang imong output is constant, no? Dili ga utro-utro. So the error is not changing. So the derivative control is useless because ang output niya is always 0. Because the derivative lagi sa constant is 0 man. Okay? So ingon dere, just because an error exists does not mean that there will be a derivative output. So pasabot wala output 0 gid siya. Nga naman kay constant man imong error. No? Ang error nimo constant. So the derivative of a constant is 0. So mao na ang limitation sa imong proportional control. That's why dili siya ginagamit alone. No? Hindi siya advised na ginagamit alone na derivative controller, but rather a combination of proportional and derivative. Okay? Even if the error is very large, no derivative actions occur. If the error remains constant, the error must be changing for the derivative control to have any effect. Okay, so ano ang pinaka-ultimate na limitation sa imong derivative control? Dili niya ma-anticipate kung ang error nimo or offset error nimo is constant. Okay? So, paano siya? Okay? So, another example, sabi niya siya. So, the addition of a derivative control to the proportional control provides the process with a faster reaction. So, pas-pas gini ang derivative control kay pag mag-differentiate ka, mura magagakuha na og kuan kanang sample, no? Na it's a very fast na sample na paspas gid ang imong kuan imong pagkuha sa sample. So but mao ni pasabot sa faster reaction to an error than is provided with the proportional control alone. Okay, so unsa man mga example? Example, kaning proportional plus derivative, so mao ning blue. Okay? Then ang kaning imuhang kuan, ang imuhang proportional output only, kanilang. Okay? Diba? And another example is okay, so maning compare niya PD and proportional only. So the initial output from the controller increases 20% using PD control, no? Versus the output of the proportional. This allows the system to respond faster to the error. So bali, Kung proportional output lang only, sana lang, no? 20%, then dugay pa kayo sa musaka. No? Sa kaya, part sa iyang proportional na output, no? So, if ever na ang error nimo is layo-layo pa, no? Hinay ang iyang reaction. 20%, then saka pa siya. Whereas, ang imong proportional derivative, sumama man ni ang katong part na proportional, ang derivative ani kaning pagsaka niya, no? Kaning step change. So dali ra kay siya. Dali ra kay siya ka step din siya, step up. Mura nga step up then linear dayon. So pasabot na advantage ang proportional derivative as compared to proportional only lang. Okay, because of this simple lang na comparison. Ang imong proportional from 20% pasaka siya, dugay pa siya kaabot sa 60%, whereas ang imong proportional derivative pag apply sa derivative, no, instant diretso, step up din siya diretso, and aya din ang proportional. So dali ra ni ma-achieve ang 60. Ang 60% based on the time na shown dere, it's possible na 1 minute lang achieve na nimo ang 60% na output. If you're trying to correct an error, siguro na ang expected nimo na set point is na dere sa 80%, assuming dali ra kay kasaka siya. Whereas ang kaning proportional only, no, para maka-reach siya og 60% output, it will take 2 minutes. Okay? May pangutana? Therefore, the proportional only control system requires 1 extra minute to match the output of your proportional derivative system. Okay? So, ibalik lang yan. Okay, so what happens when your derivative setting is too high? So, kung taas kayong value sa imong D, parameter D, na may tabo. May tabo. Oscillating ra kayo siya. Okay, so the derivative time should be set high enough so that the controller output immediately when an error occurs. Okay? However, if the action is set too high, the system becomes unstable because the response overreacts the error. Magbalot-balot siya, no? Unstable siya na output. Ano example sa unstable? Okay? So, it goes to show that this graphics, no, picture also shows that the derivative control does not eliminate the offset. Okay? So, we go now to the benefits of the derivative control. Kung PI lang siya, no, say just like atong the last time na discussion, proportional integral control, so dako kay ang overshoot. But if you're going to add derivative on your PI, so pasabot na yun siyang PID. So inahan niya ang improvement. Because of that anticipation, namin siya ability to anticipate. Anticipate man niya or ma-forecast niya ang aning sobraan na kay taas na output overshoot. So money na kanindot pag mag-add ka o derivative. Ma-predict niya ang future na output or ma-anticipate niya. The term is anticipate. Not really predict, but the correct term is anticipate. Okay, dili na siya wala man siya artificial intelligence para makaingon ka that it will or even intelligence para makapredict siya, but rather its characteristic is anticipate because of the differential of derivative action. Okay, so technically mas preferred yun ang PID, complete sila, proportional, and derivative. We're just discussing the different effects of proportional, the effects of integral, and the effects of derivative accordingly, because one way or another, there will be cases na in the system or there is over design or kaning gitawag na nasubraan na o kuan nga na particularly if dealing with kuan nga na pipe diameter. Dito system nimo na pipe is 1 inch, then ang imong final control element, let's say the proportional valve is 2 inch. Pagkadako kayo sa kuan nila, no, mismatch kayo, supposedly dapat 1 siya or 1 and 1/2, but since based on the availability, so sometimes you have to make some decisions during the installation, no, because of the time constraint, no, wala ni abot to ang kuan supposedly na timeline na i-deliver ang 1 inch na control valve. Ang katong existing na ninyo is 2 inch. So you should make a call, no, kay makasapaan ta sa management kay wala na abot ang ato ang kuan, no, completion sa kuan. So sayang ang kuan na gitawag na opportunity loss kung magdagan na ang kuan production line. So while waiting atong kuan, so why not install na lang tong available na kuan instrument. So mo nang pag i-auto-tune nimo ang imong PID controller, sometimes there will be cases na dili niya self-tune or ma-auto-tune ang values sa P, I, and D accordingly. So sometimes you need to do manual tuning. I-set ni mo ang P, kay magbuot sa I, kay magbuot sa D. Para dili kay siya ga-overshoot during when the system is running, no? So may running kanina mga cases para ma-minimize na nimo ng mga cases na unstable siya. So no, this is the reason why we have to study the behavior of P, I, and D. Dili lang na magsalig sa auto-tune na automatic lang. Kaya there will be cases na dili gid siya ma-auto-tune. Kinahanglan yung mag-manual na intervention. So derivative control is often added, no, to P and PI control system to reduce, overshoot, and dump the oscillations. So ito mag-oscillate siya para ma-dump na. So it reduces overshoot by anticipating the error. So yung ginahingan na kina-predict or anticipate the error in advance and applying the needed correction before the error becomes large. Siya sa kaning PI na scenario as compared to a PID. So complete na siya. Okay, so let's try to analyze the response of your derivative, no, response to an step input. So kung ang input nimo sa imong error is inani tawagan ni step input, because of the very instantaneous or kaning abrupt change, no, from minimum value to maximum, mo na ang iyang anticipation pod, no, as ang derivative na output nakuratan mo siya kalit og saka. So mo nang gitawag na output has large spike infinitely. So murag saka kalit. So mo nang isa sa problem in the limitations of a derivative system or controller kay once there will be a step change kana bitong ganing kalit og saka, ang output sa imong derivative makuratan pod. No, pag-anticipate niya, kaya nisaka mo siya kalit, anticipate po siya, nasaka po siya. No, so, ang tawag ng impulse. Okay? Kaya so kung mag-adto mo sa mathematics, this is a pulse. No? Kani impulse. So in mathematics, or even an advanced na communication or electronics na courses, or electrical, the derivative of a pulse is actually an impulse. Kani impulse na siya. So, because the derivative response increases as the error signal's rate of change increases. So, kalit kaya yung pagsaka. A step change in the error cause the output to go infinitely high and immediately return to zero. So, mana siya. Okay, pagsaka niya ni dire constant naman. What is the derivative of a constant? Is zero. Okay? So mana siya. So this type of response occurs because the rate of change initially equals infinity. Katong itong pagsaka niya sa kaning step change, padung man na sa infinity. No? When the step reaches its maximum value, the rate of change goes to zero. So as the derivative output is zero. Okay? So mura ginani, no? Sharp kay yung change, no? So para the derivative response to a step input can have negative. So ano ang ingon no, negative may ang effect. Para dili inana ang effect sa imong PID na system, so nag-add ang imong PID na system of kaning filter. Tawag gani filtered step input. Pag doon na kay step, pag makadetect ang imong PID controller of step input, automatic na niya i-filter. Okay, para dili mo kalit o kung sa elevator pa ni siya, no? Assuming lamang kag kalit na og ganang ang error nimo kalit og kasaka. Sao na lang ka ang output po nimo kalit po og kasaka. So para ma-prevent ng negative effect, no? Most controllers include a filter that smooths out the step change error. Kani kung maginani ka, i-convert na ito inani. So in effect, so mao naman ni imong imong step change na input with filter ni siya. So ang imo na yung output, at least nani lang. Dili siya mo saka kalit pa doon sa infinity. Kaya naman siya pagsaka. Okay? So the example shows the derivative response to an input change with a filter. The initial output is still large and still comes down to zero as the error signal becomes constant. However, the output does not become infinitely large because the rate of change in the error is not infinitely large and it would be in an unfiltered step change. Okay, so mano yung lahang additional na features for the PID controllers. Makadetect siya og step change na input, so at least convert na into step change with filter para di makuratan ang mga PID na system, particularly the derivative ladder. So question, knowledge check. No? Derivative control is not used alone. No? Hindi siya pwede na kanilang derivative. So dapat PD gid siya, PID. Okay? Hindi siya pwede D lang as shown in the block diagram. So derivative control is not used alone because it only contributes to the response when so man ang answer when the error is changing, when the error is constant, when the error is zero. Okay, so nangatulog na mo guys. So ano may answer sa kong pangutana? Hello? Madunggan pa ba ko?
Sir.
Ano sa may answer ba?
Changing, sir.
Very good. So naminaw gid mo. Very good. Yeah. So okay, sa calculus pa, the derivative of a constant is zero. So useless. But the derivative of a variable is constant. Pero pag second order, let's say, derivative of 2x with respect to x squared, may mo siya 2x. Okay? So, kanang x squared, kaya kuhan mo na, parabolic or changing. No? Pag-i-graph na nimo. So, changing, di siya dapat constant. So, dapat, the answer is, the error should be changing. Okay, kung when the error is constant, na wala siya output, the output niya is zero because the derivative of a constant is zero. So, very good. No? At least naminaw gina mo na agad nakasabot. At least isa doon ay nakatubag. Okay, let's proceed. Okay, so asa man ay kasagaran ginagamit ng PD? Mga applications. So usually, the PD control is generally used in applications that have sudden load changes or systems that normally have a long time delay between the controller when the controller applies corrective action. and when the system responds to actions. Ay pinaka very good in an example na daghan kay siya ay kung ano, variations, load variations is kaning mga temperature control system. Aside sa dugay kay musaka ang temperature, dugay kay munaog, ano siya. Daghan kasi mga load variations ang suitable na practical na example of a PD is a control system is kaning temperature control system. But for me, no, mas nindot gyapon ang kompleto, PID. Para na kay past, and para na kay present, past, and the future. So, manang PID. Okay, so maragapon, ipangutana ra gyapon niya what type of control system that use PD control because they are typically slow. So mao ni ang temperature. Kaning level dili man slow, paspas kinang musaka. Dali ra kay mapuno imong tank. So ang flow pod paspas kay ang flow rate. Pero ang temperature, especially kung dagko kay mga containers, dugay kay mo init. Okay, so minana na siya. Okay? So, doon lang man ang attendance you guys. Katong wala pa naka-attendance, so attendance. So, we review the ato ang Shinko or Panasonic na temperature controller. So, simple ra. Again, if it is a PD na system, as long na doon ay word na proportional, then it should be continuous output mode. So same like yapon, just like the last time. Nagamit ka o proportional na bulb, so inani ang setup for the 20 yapon. Dayon, this time, no, in the setting, dili sa ta mag-auto-tune. So dili ta sa proportional, sa P. So magbutang tang value sa P or the default value and followed by the D, the derivative. Ang derivative niya na parameter default is 50 seconds for our temperature controller. But then again, kung gusto ka PD lang, then you're going to set the I or the integral time parameter to 0 to disable para ma-disable na siya na function. So take note, P and D lang. Pero sa I, 0 nimo. Okay, instead na 200 seconds or minutes, 3 minutes more, so dapat is 0 nimo siya para PD. Okay? So, asa kita ato na kuan na key para mo-adto ta sa atong IP, na I, na D, o na auto-tune. So, you're going to press up and the mode key at the same time or the set key at the same time kung ano na nimo para makasulod ka aning auto-tune, kaning na P na parameter, na I na parameter, na D. Okay? So, na may pangutana? Uy, mananata. Okay? So, we're done. So, kadjot ra tong mas maaning dali ra tong moment para dali ra ta magkasinabot. Okay? So, kinsa pa tong wala naka-attendance? Okay, so jump tayo, mag-countdown ako before ako stop ang recording. 5, 4, 3, 2, 1. So wala na yung mga attendance. Uy, napagin ni Apas. So another 5, 4, 3, 2, 1. Wala na. So, na may pangutana? Before I get to stop the recording. Okay, so remember lang na pag P, present na siya. Pag I, past. Pag D, future. Dalira. Dalira siya. Kung mathematically po, ang P kay proportional man na siya, so linear. And pag mingon kag I, it's the sum or the accumulated errors. So appeal to ang previous na mga errors, accumulated gani. So man ang past. Pag mingon kag D, derivative. So differentiate nimo, so man ang future na anticipating the change, no? Okay, so kung wala na may pangutana, stop the recording na, then pamay na. Uy, napay ni Hapas. Ngayon na pa ba yung wilain mo, Apas? 5, 4, 3, 2, 1, 0. Okay, bye-bye.
Yes, sir.